scientific fields we will delve into at Trieste Next. This is the central theme of Trieste Next, featuring over 100 events in English and Italian, the Literary Award for the Scientific Book of the Year, and 70 activities for schools. More than 300 internationally renowned speakers will be in Trieste. And don't forget to visit the 40 exhibition spaces and open labs in Piazza Unita. Before we welcome the guests of the next event, on behalf of the organizers and co-organizers, I would like to thank all the scientific institutions of Trieste, City of Knowledge, as well as the institutions that collaborated with us. A special thanks goes to the festival's main partner, the partners, and content partners for their crucial contributions. Thanks also to the media and technical partners. Lastly, a heartfelt thanks to the 200 volunteers who made this edition possible. One final note. I'd like to remind you that the next session will last 75 minutes, with the final 15 minutes dedicated to your questions. Please also remember to check the updated event schedule on www.triestenext.t, which you can access via the QR code. Enjoy the event and have a great festival.
Good morning and welcome to this presentation. I am Alberto Dellacasa Bellingegni and I'm an engineer at Prosthetic Center of the Corso di Budrio, at the moment employed by the Italian Institute of Technology. Today, I'm about to present you this presentation, actually, which is entitled Prosthetic Rehabilitation Research from Osseointegrate Prosthesis to Assistive Robotics. Well, despite the title start from Osseointegrate Prosthesis, I decided to switch upside down at the presentation. So we will start from Assistive Robotics and then end the presentation with the Osseointegrate Prosthesis. But before moving to the next slide, okay, let me first introduce you the Centro Protesi INAIL, where I work and where we do research. The Centro Protesi INAIL, the Prosthetic Center, is a part of INAIL, which is the Italian National Institute for the Insurance Against Work-Related Injuries. And thanks to its ramification all over the Italian territory, every year, thousands of people, thousands of patients converge to the Prosthetic Center for accessing to its services, which what concretely we do at Prosthetic Center, we process and customize prosthetics and ortheses. We do operation like training for teaching the correct use of orthopedic device. We develop prosthetics and aids for sports. So we take part to the Paralympic Games with the national Italian teams. We also provide psychological supports and other personal services, as well as orthopedic aids and vehicle customization for all the people that suffered in work-related injury, or also other people, also the people that actually suffered a limb amputation due to other reasons that are not related to work. But in addition to all these services that the Prosthetic Center offer, well, we also are active in the research field. Research in bionics, prosthetics, and osseointegration. Okay. The research in Prosthetic Center INAIL is divided in project plans, okay, which can be normally of short and medium term, which aims to develop technologies that in a reasonably short time can produce these devices that can be placed on the market. And so all the people that are suffering a limb loss or any type of injury or need a certain type of rehabilitation can exploit these new technologies in a short time, during their lifetime. Although we also face and we accept the challenge of long-term project plans, which will see the outcome in the next years, the decennial, 10 years or so on, which basically concretely are high-profile scientific challenges. We are talking about frontiers, cutting-edge new technologies, neural interfaces, connection with the direct nervous system, the central nervous system, and so on. In these project plans, we We take care of different fields such as upper limb prosthetics, lower limb prosthetics, rehabilitation, robotics, surgery and rehabilitation, and evaluation systems also for evaluating, for understanding what the subject really need. Thanks to the Centro Protesi, because thousands of people every year access to its services, well, that creates a big pool of subject patients for which and with which do research activities. And thanks to that, we are able to proceed and provide and create research using a user-centered design approach, centered on the user's need. And concretely in what we are talking about, here I want to show you what the user-centered design workflow is. How can we put the subject, the final user of our technology, at the center of the design development? Well, basically, the starting point, when we want to create a new device, a new technology, what we do, firstly, we analyze the experience we have at Centro Protesi INAIL, what we can do, what we've done in the past. We check what is available on the market, but mostly we subministrate to our subject, to a pool of subject, survey and we organize focus group. So from those information, we are able to detect what the final user want, what the final users need, and how the technology can intercept these needs, okay? From all this information, which basically creates the background for our scientific development, we are able to identify functional specification which then are translated into technical specification. We take care of then, once we identify the technology that is necessary for obtaining certain function of our final device, then we create a prototype. The first prototype, so there is a phase of design and development. Once we obtain the prototype, we undergo a phase of clinical trial and start pilot study. And if there are any problem with that, or they need customization or other adapting system, we can switch back to the design and development phase, create a new prototype, adjusting the technical specification as well, in order to get to the real goal of our research in a cyclical way, okay? At every iteration, we get closer to our goal. How we do that in the research in prosthetic center? Well, we don't do everything by ourselves, but actually we can relate and resort to a research network, which includes the local district of the National Health System, such as Istituto Ortopedico Rizzoli, several research institutes, such as the Italian Institute of Technology, for which I work, the CNR, Consiglio Nazionale delle Ricerche, and several universities. Each one of them, at the same time, has their own research network, with which we can, attain to their research network in order to have partner and sub-partner, national and international. What is the role of INAIL in all these research networks? Well, is responsible of design and co-design the research projects, manage and coordinate the activities in order to be sure that every single one of the partner of this team, which is basically a multidisciplinary team, will converge to the same goal, okay? We define the functional specification because of the user-centered design approach. And then we take care, and sometimes, often actually, of the technological development and of clinical studies. And thanks to the synergy among the research network, it is possible to carry out multidisciplinary research activities, including clinicians, doctors, bioengineers, any type of engineering, the field of engineering, electronics, mechanics, robotics, automation, and stuff like that. And also we take into consideration the neuroscience, not just the engineering aspect of it, but also the way in which actually we can study how our brain works at the same time. thanks to this research network, at the moment, currently there are 18 bionic projects, bionics, prosthetics, and evaluation systems within a 36 3 years horizon, using 8 main partners and 14 sub-partners, both clinical and technological. We divide our research projects at the moment in lines, okay? We have 5 different lines: robotic rehabilitation, which has the listed project like Feather Exo, Clinic Exo, BioArm Next, and so on. Lower limb prosthetics, upper limb prosthetics, surgery and rehabilitation, and evaluation systems. Well, in this presentation, I would have really liked to present you every single one of those, although the project has just started, and despite they are in continuation with the project we had in the previous years, I've selected a few of them in order to let you see what we achieved from the previous project and where we are moving with the new one. I decided to divide the presentation again in 3 subcategories, which are assistive robotics, bionic interfaces, and osseointegrated prosthesis. So now let's move forward to the assistive robotics. I want to show you what is our experience, what devices we developed as outcome of the previous project. And so let's go ahead and let's see the first one. The first one is the float. Float is a robotic device for post-traumatic and post-surgery rehabilitation, which, as you can see from the picture, is composed by multiple parts, which is a control unit, obviously for controlling the robot, a mobile cart, which takes care of the weight compensation, you know, it keeps standing the entire structure, and an exoskeleton, which covers shoulder, elbow, and elbow. So basically, from the back to the forearm. It is used for rehabilitation because no, it doesn't want to substitute the therapist, but with these devices, we are able to repeat the same movement without any change. And we can use that also for evaluating in a quantitative way the performance and the improvement of the subject. Okay, these devices, the float device, offers a weight compensation in order to, you know, facilitate the free movement of the robot. Okay, and so the subject can be helped to perform certain movement that he couldn't do without help. Okay, but it can also be operated remotely in both in a kinematic mode and a trajectory mode. Kinematic means that basically the operator moves the robot from the computer, and the certain movements are performed by the robot, and the user inside actually is, you know, passively moved by the robot. And the trajectory mode is a system in which actually the therapist performs a movement with the robot records its trajectory that the therapist done. So we use the therapist as an active controller of the robot. It records it, and then it plays it, you know, continuously until there is a new change needed. The next device I want to talk to you about is the twin exoskeleton. Okay, what is an exoskeleton? Well, it's a device, a robotic device that, well, concretely, it's used for people that cannot walk anymore to walk again. Okay, I want to be clear, it's not a device that wants to substitute the wheelchair. It's not its main goal. It's still a rehabilitation device, because for the people that actually have lost the use of legs, there are a lot of problems that are related to not just the possibility of walking again, but the lymphatic system stops working, the blood clots, you know, the circulatory system has a lot of, you know, not moving creates a lot of problems to those systems, which are naturally solved by walking again. Okay, so the action of walking has a therapeutic goal as an achievement. And this is the new exoskeleton, the last evolution of our exoskeleton, which is visible at our stand in Piazza dell'Unità. Has a remarkable weight of 21 kg, which is a remarkable result, I have to say. 4 motors, 2 by sides, that can express a maximum force of 140 Newton meters and a maximum speed of 1.7 kilometers per hour. To be used, it requires the use of crutches, okay? And how does it concretely work? So basically, the user leaning forward triggers, thanks to an accelerometer, IMU sensors and inclinometers and other sensory that is on board of the device, detects that the inclination is happening, and that triggers the start of the gait, or the step, okay? Lift the hip, move ahead the knee joint, and performs a step. And that is repeatedly obtained. Let me show you with the next slide. What in this slide we'll see also in the video, we'll see how that actually performs and actually works. What functionalities we can provide in order to achieve a good rehabilitation, the best rehabilitation possible. Well, we have 3 working systems, rehabilitation systems. One of which is called Cammina, which forces indeed a working pattern which is defined by the therapist. Okay, the user at the moment is passive, so it's indicated for people that cannot use at all the legs. It is, although required, a certain control of the upper body, for balancing purposes. And in this case, that is pretty much something incredible, that a person that could not walk at all is standing up. For a person that cannot walk and cannot stand up is a great achievement. Then we have the second functioning mode, which is retrain, which forces a pattern only in a particular phase of the gait. For instance, we have a subject that moves very well the hip joint, but doesn't lift the ankle, or doesn't lift enough the knee when it's done. Well, we can analyze that movement and program the exoskeleton in order to give help only when it's needed, in order to focus the rehabilitation process where is needed, not in all the movement, like in the Cammina, for instance, but only in certain points. And the twin care, which is used for people that has an injury, I have a disabilitation only in one leg, not in both. So it forces a pattern only on the leg that is injured. As I said, a lot of these, all these devices carries in a lot of sensors on board, sensors that are used for the working system, for detecting when the inclination is occurring, what position a certain motor is, encoders, accelerometers, gyroscopes, gyros, and other sensors, which can give us also not just an estimation of how the system is working, but can give us back a performance evaluation. And from that, we have designed a new type of exoskeleton, which we call the Twin Med, which is an exoskeleton that aims to do exactly that. Instead of being used just for rehabilitation, we mounted on board several more sensors, and we want to use it in order to have a clinical analysis of the gait, basically a gait analysis of the performance of the user, in order to have an evaluation and proceed with the best treatment. That is a performance feedback. And from that idea actually comes one of the new projects that just started, which is Clinic X, which basically has the aim, which aims to provide an HCA analysis of exoskeletal devices. Okay, that is for knowing a technology and being used all over the world. New devices such as exoskeleton or robotic devices in general basically are evaluated using quite old scales, especially, and sometimes those scales are not objective. They doesn't use number. They use a survey and and the evaluation scales that are affected by the user, both the subject, the patient, and the administrator opinion. Okay, that creates a bias and doesn't allow a perfect and precise estimation of the HTA. But thanks to the fact that with TwinMed, for instance, and the flow device as well, we can have a numeric estimation of what the performance, the residual performance of a user are. We have numbers to operate a precise estimation, as engineers likes, all numbers, not good, bad, not so good, you know, but just numbers to have a precise estimation of what the HTA is, and possibly help to show how these devices are really, really, really important into the rehabilitation, and knowing the HTA, which is also as an economical index, well, aim to spread the use of these devices all over the world. Let's move ahead into our next chapter, which takes care of bionic interfaces. We are talking about interfaces, and we move slightly to the upper limb prosthetics. And just for the one who doesn't know how our prosthetics is controlled, well, the state of art or upper limb prosthetics is represented by the myoelectric control. Using two electromyographic sensors, such as the one showed in the left or upper left of the picture, we are able, which are placed, on the flexor and extensor of the wrist, we are able to obtain two independent signals. Why those signals are independent? Well, is because these two muscles, the flexor and the extensor of the wrist, are an agonist-antagonist. Once the upper one is contracted, the lower one is relaxed, and vice versa. As shown in the video, we associate this movement of the flexor and the extensor of the wrist to opening and closing motion of the hand. The same can be done with a transhumeral prosthetics device using the bicep and the tricep. Okay. In case of a transhumeral amputation, obviously we might have more active joints. Okay, elbow and wrist and hand. And in this case, though, we have still two control signals. Okay, that is kind of difficult because with two signals we can control one single degree of freedom. Okay, but now we have a prosthetic device which is 3 degrees of freedom. Okay, how can we switch? How can we control the entire prosthetic device? Well, for this goal, we would utilize a control strategy, which is actually an active limb control strategy, which uses a trigger signal, which is achieved by the co-contraction or the use of external mechanical switches, for instance. But the co-contraction is the simultaneous contraction of both the trigger, the target muscles, in order to switch the active limb. So I'm controlling the elbow in this moment, co-contraction, beep, I move to control the switch. And now I move that. Co-contraction again, now I'm controlling the hand. Co-contraction again, and then back to the elbow. Well, despite being extremely robust, because it's robust, well, this type of control is slow and unnatural. Just think that for controlling the hand, you are flexing and extending your wrist, okay? Or even in transhumeral prosthetics, you are controlling the hand, so controlling your bicep and tricep. Definitely not physiological. It is not possible to control with this, with the myoelectric control. It's not possible to control more than 1 degree of freedom at the time. We cannot control wrist and the hand together at the same time, okay, simultaneously. So, for instance, a very simple task, which would be like you eating, for instance, moving this elbow, wrist, is a combinated gesture, and it's not possible to achieve it with the traditional control. I mean, you can, but you need to be trained for that. The user needs to learn how to use the prosthetic device, how to eat again, and definitely, and well, there are a lot of problems that makes it very slow. Think about, you have to first use it, then fix. It's not nice. There are solutions for these problems that the research produced all over the years. And while the first and non-invasive one we are developing at Prosthetic Center relies on pattern recognition, which is a machine learning algorithm that aims to detect the user intention. How does it do that? Well, basically changes the paradigm of the myoelectric control, substituting the two electrodes with an array of them. So we don't have any more two electrode places on target muscles. We have an array, 6, 8, 10, that are placed all over the stump, okay, on the residual muscles. And it exploits a weird phenomena, interesting phenomena, which is the phantom limb sensation. In 70% of the cases, after an amputation, the phantom limb sensation remains, okay? And that is the sensation of feeling the part of the body that is missing still attached to your body, okay? Not just feeling it, but the users, the patients can control it. They can move the phantom limb sensation, okay? And when they move this phantom limb sensation, this phantom limb, it creates into the residual muscles contractions, muscular contraction, which are extremely similar to the one we would have with the real arm present. So as you can see in the video, we see my colleague, which we are using the first prototype of an algorithm that I designed years ago. Well, it works. If you can see, the hand is copying, understanding what the user is performing through the muscular contraction, which is recorded by the electromyographic sensor as array placed on the forearm. Well, if that works for a standard user, well, definitely can work also for an amputee, as we can see in the picture on the right, okay, in the video on the right. We extended also the control of the hand, not just to the hand. We extend the control of this machine learning, this algorithm, not just to the hand, but to different limbs. So here we can control both the opening and closing of the hand, but also pronation and supination of the wrist, as well flex extension of the wrist, which is interesting. Naturally, more degrees of freedom you want to control, more grasping, more classes your pattern recognition algorithm has to detect, more difficult the control is, because it becomes less and less robust. What can be done? Well, these algorithms can be trained to be robust. The user itself can actually improve his controlling skills, because these algorithms actually works on a statistical basis, and they recognize a contraction pattern. And in the very beginning, if we want to perform a certain pattern, it's hard to replicate the same movement. But with training, with the more you train your phantom limb in moving, it's observed that actually the performances increases. So there is a symbiotic relationship between the user and the technology, okay? They both adapt on themselves until they find a perfect match. And well, can we just use the electromyographic sensor for performing this type of algorithm? Well, the answer is no. Actually, those algorithms are not related to any type of sensor, particular sensor specifically. And actually, that came the idea of iHarness, which is the new prosthetic hands, prosthetic arm, let's say, in which actually we decided to hypersensorize it. we decided to put every type of sensor there is inside. There is available gyroscopes, accelerometers, cameras for video detection, HDMI electromyographic sensors, touch sensors for the skin, the palm, the fingers, and we want to use all the information to perform a sensory fusion, a data fusion, and train these algorithms in order to understand, first of all, which one are the interesting one, which one are the one that are really affecting the control in order to be robust and reliable. And as we can see here, that actually, and we also wanted to improve the training system with using virtual realities. On the left, we see what the hands can see. Actually, this grasping performance is obtained using an object detection from the camera, okay? And the release is performed by the user, and it's quite interesting. On the right, on the contrary, we see the user performing the mirror box, okay? What is called basically using the VR for improving the phantom limb sensation and controlling and training in controlling a prosthetic device. And we use both ends, okay? Because visualizing them actually helps the brain to control the muscle. It's a field of the neuroscience that is really interesting. On the bottom right, actually, we see the high-density electromyographic sensors and pattern recognition. As you can see, we can detect a lot of classes, okay? A lot of classes for our artificial intelligence system, and is able actually to control a virtual hand, okay? Well, that is what I just presented is a way of controlling prosthetic devices without being invasive and exploiting artificial intelligence. There are other ways also for enhancing the control of prosthetic devices, but are invasive. Okay, invasive means they require a surgery. Okay, a surgical treatment. The main one, the most famous probably, is the TMR, target muscle reinnervation, which is a surgical procedure that aims, you remember the two target sensor, two target muscle, agonist, antagonist, that can be contracted in a separate way, okay? The problem that we cannot control more degrees of freedom the prosthetic device at the same time is because we have only two. Well, this surgical treatment aims to multiply them, so have 3, 4, 6, and so on. How we achieve it? Well, a part of a muscle which is destined to atrophy because it's not used anymore, such as in case of shoulder disarticulation, for instance, the pectoral has no load, so it's a muscle that is destined to atrophy, to reduce in size. Well, what we can do is take that muscle, remove all the nerve connection, the natural nerve connection, then we take the nerves from the nerves that are destined to go along the arm, such as the ulnar, major, those type of nerves, and they are attached to certain places of the chest, of the muscle. In this way, what we achieve, we achieve the fact that the muscle becomes a bioamplifier of the neural signal, okay? And they become independent among themselves because the muscle itself is then divided into pieces and into 4 parts, let's say. In this case, it was divided in 5, 6 parts, and thanks to that, the user now is able to control the prosthetic device, moving. The video is not great, but something you can see is deformed. But you can see actually that is moving more than 1 degrees of freedom at the time, okay? Because those 2 signals are independent. So we can have one signal delegated to opening the hand, controlling the hand, one to the control of the wrist, and one to the control of the elbow, and even the shoulder. Similar treatment, okay, but not focused on the control, okay, but aims specifically to the feedback restitution. Feedback restitution is an important field because well, actually helps to feel the prosthetics as yours. Okay, because the main problem, one of the problems that actually the prosthetic hands has is that they doesn't provide a feedback. So you tend to feel it. There is the tendency of feeling it like a tool instead of part of your body. Because if you can feel the technology that you're using, you have an embodiment with it, and you really feel part of it. And so the literature came out with this technique, which is called the targeted sensory reinnervation, which is similar to the TMR, but instead of applying those nerves that are destined to run along the arm to the muscle, they're attached on upper layer of the skin, lower layer of the skin. The nerve then grows under the skin, and as you can see, you can map. They grow, and once you touch the skin on top, it gives back a feedback that is, reconstructed as coming from the thumb, index finger, the ring finger, thumb, and all the finger of the hand. And not just that. And that is really interesting. Moving even more invasiveness, talking about sensory feedback. We did experiments and projects that aim to have an interface with the central nervous system, okay? With the central nervous system. And for that we used internal electrodes, okay? Which can be normally of two types, massive simplification, but mainly two types. One is the times neural electrodes, which are like little needles that are inserted inside the nerve. But those type of electrodes suffers mainly from a massive problem, which is the foreign body reaction. Okay, those electrodes can be used for a certain period of time. After that, normally there is a foreign body reaction that actually covers the conductive part with isolant materials. So there is no way more to perform a stimulation, okay, a stimulation of the nerve in order to start an active potential and elicit a feedback sensation, a sensory feedback sensation. In order to overcome this problem of the times electrodes, the CAF electrodes have been came out to the market, that's available, and those actually works in a different way. They tend to induct the action of potential instead of pushing current into the nerve. We're talking about millicurrents, and that should overcome the foreign body reaction. Actually, delays it for a very long time. This is an experiment that we did, in which actually we performed an interface with a neural interface. Basically, the user at the moment, thanks to the sensors placed on the fingertip, is able to feel if the contact with the object through a direct stimulation of the nerve, and feeling if the object is sleeping, and perform tasks and require sensibility, such as the one showed in the video, feeling actually something of what she was doing. What are we doing now in the new projects on these type of scenarios? We started the project BioInterconnect, which aims to investigate bidirectional multimodal interfaces for improving the feedback in both the non-invasive and invasive scenarios. What means that basically we want to find the combination of all the sensory feedback, or provide a device that actually can allow the user or the therapist or the researcher to investigate a multimodal combination of different type of sensory feedback, which might be visual or audio feedbacks, basically an LED or a beep, a buzzer, or also thermal feedback. Okay, we have a project that actually investigates that. We place a sensor, a temperature sensor on the fingertip of the prosthetic hand, and then in a target area of the prosthetic device in contact with the stump, we give back the sensory feedback using, you know, a Peltier cell or water system, hot water system, in order to mimic the same temperature felt on the fingertip. On the invasive side, we are trying to perform, it's quite a big challenge, but we are trying to obtain an implantable neural stimulator, okay, which is composed of two pieces. One is outside, okay, the body, and one inside the body, and the power without batteries, and they are powered. Once powered, the outside actually has a battery, and powers the inside part using wireless power transfer. Okay, and also they communicate together using a Bluetooth BLE connection. There are a lot of issues, not issues. Well, on the desk you can do everything, but then when you want to design something that goes into a human body, there are regulation, lots of normative, lots of ISOs to follow in order to be safer, first of all, and in order to not, irradiate the body with a lot of energy that is not healthy at all. So yes, it's a concept idea. We are testing it, and we are moving also on that front. As you remember, there is one of the main problems of these neural electrodes is the foreign body reaction. Well, we started also another project called OptiNerve in order to try to overcome that using not just an electrical stimulation, but using optical fiber instead. Okay, so an infrared impulse. Okay, because it's proven that the infrared impulse over the nerve actually can start a potential action. Okay, and varying the frequency and the wavelength of these impulse, it is possible to make the light penetrate the skin or the nerve or the tissue, the reason, for up to 1 millimeter. That means that we can start an action potential without getting into contact with the nerve. Okay, and potentially that actually means a chronic implant, potentially. Although there is how the action potential is performed, is achieved, what are the chemical and biological reaction that creates this actual potential are not fully understand. So that will be also the chance for investigating those type of scenarios. In order to understand what sensation, what are the parameters, because there are a lot of parameters to set up for the light, the impulse, frequency, and stuff like that. In order to understand what are the parameters of this light impulse for performing a certain selected stimulation, like touch, slippery, pain, will be used also, in this case, artificial intelligence, in order to understand which are the parameters involved into the sensation. Let's move to the final part of this presentation, and let's talk about osseointegrated prosthesis. Well, nowadays, the socket, our device, the socket or prosthetic device, are the way we connect the prosthetic device to the residual limb, okay? And there are cases, actually, for which it's not possible to create a comfortable socket, okay? Because we always think that the stump, the amputation is nice and clean, neat. It's not always like that. The clinical side, as you can see on the right, for instance, those are residual limbs that are hardly you can make a comfortable socket, and if you can, it's hardly able to provide any signal for the control, and is a tough scenario. Those are tough scenarios. How to overcome these issues? Well, the osseointegration might represent a solution. Okay, osseointegration is a procedure that is similar. Okay, allow me the term, similar to a dental implant. Okay, and what is performed basically is we have a connection with the skeleton, basically, and There are several advantages on these type of treatments, such as, well, you can perform a quick lock release. There is no use of the socket, no need of the socket anymore. So all the issue related to the socket, such as excessive sweat, inflammatory reaction, allergic reaction, and any type of that, are immediately solved. There is an immediate load distribution over the anatomical axis, because you are using the structure of your body that are actually designed and evolved for sustaining that type of load instead of distributing it over a surface. There is the creation of what is called osseoperception. Basically, is a feedback that the bone itself, when you have a contact with the bone, you feel the contact with the ground more clearly with respect of having a socket. And you can perform it for both upper limb and lower limb. And that's what we did in the past projects. How is it performed? Well, exactly as you imagine. The treatment involves 2 surgical procedures. During the first one, a titanium fixture is surgically attached to the skeleton. Then a second that occurs 6 months later, after there is a certain recovery time. A skin penetrating abutment is inserted into the fixture, okay? And that represents the attach point for the new prosthetic device. And here we see what is the outcome of this treatment in a prosthetic, in upper limb prosthetics. Okay, the subject also received TMR, which is the technique for not amplifying, but for having the possibility of controlling more degrees of freedom at the same time. And the not using the prosthetic devices actually has, for upper limb prosthetics, has another advantages, which is to avoid completely the electrode shifting. When you have the electrodes, the MG sensors, which are placed into the socket is attached to the elbow, for instance. Every time you move the prosthetics, those electrodes moves, the sensors moves, and moving them changes the signal achieved. And for instance, performing operation like the one on the left that is showing, basically controlling the hand, having your elbow up above your head, is pretty much impossible to achieve it with a traditional prosthetics. Okay, because the electrode will move, the control will be affected by noise, and a lot of complication. Now here we see instead the same treatment applied to lower limb, to leg, and you can see that actually the weight distribution is perfect. Is walking. You pretty much cannot say that he's wearing prosthetics. The same happens with the normal prosthetic devices, because the users actually become very good in walking with them, and you need to know that they are wearing prosthetic devices. And that's it. That is really interesting. Well, somebody might ask though, why we don't perform this type of operation all the time? Okay, why since it's so good, why is not performed continuously? Well, because well, first of all, we have a fixture inserted into your bone, okay, and we don't know how these implants concretely will behave. We have an estimation, but we don't know for sure how these implants will age in time. With an aging population, we have this treatment, your bone structure becomes lighter. How that system will affect you when you become old, and that's why those are treatment that before being declared sound and safe takes a long time and lots of studies on them. So what we're doing is improving the population of these subjects in order to amplify the studies, but the advantages are remarkable and undeniable. Well, the osseointegrated implants normally available on the markets comes in different sizes, discrete sizes, okay? And that means that when they are inserted into the bone, while the orthopedic has to drill the bone in order to adjust it to the shape of the implant. What we try to achieve with the osteocustom project is well, we can start from a CTA scan, okay, reconstruct the bone structure and the medullary canal section, and maybe we can design a fixture and abutment that is patient matched. So instead of minimizing the work of the surgery, because if you can design an abutment, a fixture, sorry, that can mimic the shape, because the canal is not straight, as certain bends, is a kind of tricky shape to mimic in the in the 3D view. But if we can make the fixture of the perfect and optimal shape for that type of bone, we can minimize the work of the surgery. We can minimize the bone that needs to be removed and filed, and possibly create a better osseointegration. Because what happens is with these materials, the bone actually grows on the implant and becomes a fusion. Those are titanium, titanium alloys, and other materials. There are several materials. And for doing that, though, because of the complexity of the shape of this fixture and abutment, different shapes and so on, we decided to rely on additive manufacturing technologies, okay, which can print these type of materials, biocompatible metal, robustness, and stuff like that, and so on. Yeah. The same time, at the same level, pretty much in the same way, we tried to take care of what is a partial amputation of the thumb, okay, which is a very tricky amputation, because simplification, not always is possible to create a prosthetic device for it, and if it is, it's going to be most likely an aesthetical one. That means you cannot apply forces on it because there is no attachment point, okay? So we decided maybe we can perform the same operation for the lower limb, like osteocustom, and do something for the partial amputation of the thumb. We start from the CTA scan, we detect where the bone is stronger, we can design the size of the screw, okay, that the fixture that actually has to be inserted and implanted, in order to we can test different shapes and surface treatments in order to have a better osseointegration and create something that is also not just aesthetical, because the prosthetic device will always be aesthetical, but actually can be used for applying force and forces. We had these implant designed and applied in the adjoint project, and we just started the adjoint 2 project, which actually will investigate these type of implants, okay, and possibly also they take care of the fact that we will try to design prosthetic thumbs, for instance, that incorporates in them some touch sensory, which is a heat, which can be sent back to the thumb, for instance, with a vibration or with thermal stimulation, and possibly extend the adjoint, which is specifically aiming to the thumb, to also the other finger of the hand. Now moving still with osseointegration and for lower limb, and continuing the results of the osteocustom, which is the custom-made patient-matched fixture and abutment, which we achieved, and we will observe the outcomes in the next years. Started now the project OsteoAMI, which aims to increase the population of the people that received an osseointegration treatment for lower limb, and actually aims to to perform also an agonist-antagonist myonerval interface for aka AMI. Basically, what is AMI is a surgical technique again, which connects together two agonist and antagonist muscle. Okay, seen sometimes in literature for upper limb, connecting the bicep and the tricep. What is the main goal of that? Is giving back a sense of proprioception. Okay, proprioception is the feeling, simplification of the position of your arm. Okay, if you close your eyes, you feel where your arm is, even if you don't see it. You know where is your position. You have this, you sense it. Okay, when you don't, you have a limb loss, you suffer a limb loss, that sensation of the phantom limb can become confusing because there is no feedback. Your brain uses the sensors he has into your muscle. You can feel your muscle contracting, and naturally, when you contract an agonist-antagonist, one contracts and the other extends. If there is no connection between the two, the brain receives contradictive signals and can get into confusion. So the main idea, what is it? Is, well, let's connect them together. So when one connects, the other follows and moves in a more natural way. Okay, we will try to achieve this surgical technique on transtibial amputation. Okay, as showed in the video. This is an experiment that has been studied in USA by the MIT a few years ago, but we decided to actually perform it and have our case study over here in Italy. So is kind of ahead of time. We will also, at the same time, as I said, check the results of the outcome of the osteocustom procedures and the osseointegration. And that was my presentation. Thank you for the attention. If there are any questions, please move forward.
Okay. Thank you. And first of all, very interesting presentation and very outstanding work. I was curious about the first, I have two questions actually. In the first part of the presentation about the gait trainer, you said that you are developing quantitative metrics to assess the correct functioning. Can you give us an example? Because I feel like in the first case, when it's patient dependent, it's something like, yeah, it feels good, it doesn't feel good. But in a quantitative way, what do you measure practically?
For instance, the speed of the movement. For instance, I have a sensor that places like an encoder. My exoskeleton measures the angle of my limb. So I can say, oh, okay, perfect. The patient is doing it on himself, moving at 3 radians per second or 2 radians per second. That is a number. So we know that actually the therapy, the goal is 20 radians per second. Okay, I know that I'm starting from 3 and I get to 20. So that is an objective number that can be used for estimating how good is the technology. While the therapist is saying, oh, well, comes the first therapist, yeah, it's stiff. 1 to 10, how stiff it is? 5. Comes therapist number 2, same subject, stiff number 6. That is objective. One said 5, one said 6. The encoder, the sensor, will say always the same number, and is not biased by the user opinion. Both the therapist and the subject who might have the same. How did you feel the movement? I was on 1 to 10, 6. Same therapist, changed the subject. How was it? 5. An exoskeleton solution used for evaluating the status, the starting status, and the development of the treatment of a subject is really interesting because it gives you numbers, and with numbers you can do everything.
And about the intraossea prosthesis, you said that you have to basically drill the bone to insert the.
You don't have to drill it. You have to adjust it because there is a medullary canal inside. There is a hole. It's hollow inside the bone by
Okay.
itself, but the implant comes in sizes. Okay.
Okay.
In order to fit the most of the population, but they are standardized sizes. Every single bone of every human is different, has its own particularity. So what the surgeon has to do is to, tries to insert it and tries to, bend it, open the canal a little bit more so it can fit in, and then literally hammers it in.
And how, I mean, are you not afraid that in time, like the bond between the bone and the prosthesis, like falls off and the prosthesis can just.
No. Those
How do you
materials.
say closely attached? I mean, like if I pull it, it doesn't come out.
Well, that doesn't happen, okay? But yeah, I'm not a surgeon, I'm not a clinician, I'm not a doctor. But when I've seen the procedure when they insert it, or you can see it on internet as well, is hammered it in, okay? Hammered, okay? So it fits tight. Plus, those materials are actually designed, okay, in certain materials in order to let the bone grow, which grows and attach to the implant, so it doesn't fall off. Okay, there is always the risk of an infection and a rejected implant, but those are not, our problematic scenarios are not the something that you can foresee. Okay, it can happen, but I'm not a clinician. I don't know how those things happen. So I've seen now that the implant is inserted, and I can guarantee to you that it is tight. It is tight. But using standardized sizes actually creates that the surgeon has to, to adjust it a little bit in order to fit better. If we can design it with the shape of the canal, the medullary canal, well, we reduce the damage of the bone, and that's something that is good. Another question?
Hello, I have a question regarding assistive robotics. I would like to know if there are important differences between the exoskeletons that are used for rehabilitation and biotechnology and the exoskeletons that are developing now for reducing the efforts of workers in hard jobs and heavy industries. Thank you.
Yeah. So in prosthetic center, we take care of exoskeletons that are used for rehabilitation, not for augmentative performances, if it makes sense. The exoskeleton that are taken part by another part of the research of INAIL itself, which is work on the prevention of the work-related injuries. But the technology is similar, although in one case we are working with a subject, a patient that cannot use the legs. So the entire weight, the balance, and the step motion needs to be supported. With the exoskeleton for work use, for performance enhancing, we have a normal body. Okay, so the technology is different. Okay, we might have still some motors, but most of the coordination and the balancement system will be achieved by the user itself. Okay, and while on the rehabilitative robots, they aim to the movement in order to be natural and doesn't take care of the weight at all. So they are conceptually are similar, but both technologically and really in the way they are controlled is completely different. There are two different fields of the same exoskeleton field.
Hi, thank you for your presentation. It was very interesting. I have a question, which I don't know how nice it is, but how long until, I mean, except for the exoskeleton, which I'm assuming you are actually using it with patients for rehabilitation. The others seems quite an experimental level, so
Yeah.
you're still, you know,
Most of-
improving them, writing papers. I mean, there's a lot of research going on. But how long do you think before those can be used by the wide population, and how expensive will they be? Let's not take into account the costs of research, because otherwise there would be like millions and only for few. But is it something that you think we might reach in the next future, or are we thinking about more than 20 years ahead?
That's my opinion only. So I don't know. I hope that it will be available tomorrow, for instance, but I don't foresee it coming in because those are experiments that takes a long life study. The subject needs to be studied for its whole life, you know, and more than one, for having a statistical basis on which to evaluate the science. Okay, so as I told you, the osseointegrated implants, we don't know how we have an estimation, we have a foreseeing of what's going to happen, but in science you need numbers, you need a study that proves that a certain technology is safe, or its benefits overcomes the negative sides. And at the moment, the population of those implants is not so wide for being able to claim that this technology is ultimately good. We see it is good, but as a scientist, we need to prove it. It's not just enough to say, oh, it's good, it's great. You need to prove it, and we are submitting to these people, to a wide population. Wide population, who's taking the responsibility of saying it's sure? Something happens, and these osseointegrating implants have a whole other level of risk assessment. With the prosthetic device, if you hit a hole and you fall down, the prosthetics, worst case scenario, falls off. Okay, and now you have well, something inserted into your bone. If you fell in a bad way, the bone breaks. That is a risk hazard. What's going to happen? We don't know. Okay, it's hard. We see how good it is, and but before having something safe, when I provide you something that needs to be safe, cannot be, you know, hazardous. And those volunteers that actually undergoes the treatment are pioneers in that. That is undeniable, and we are all great for that. But it's not just the technology that we can say, for instance, from 20 to 30 years old is safe. Okay, and then what do? We remove the implant, because when you get 35, like me, you remove the implant. You cannot do. I mean, it's not wise to do it. It's another surgery, another treatment. It's just for being sure that the technology is safe. You need scientific evidence, and we don't have them yet.
Completely unrelated.
Awesome.
I was curious, how did you start working for INAIL? Because it kind of came as a surprise that they had like a research center.
Yeah.
To me, at least. So I was wondering how like the hiring process worked. If you want to answer this, it's just out of curiosity.
Well, okay. INAIL has a prosthetic center since 1960. Okay, and is developed for the people that actually suffered a limb loss as a work-related accident. Okay, and it developed in order to provide the best and most advanced technologies into the prosthetics for its users. How did I start working that? Well, as I told you, at the moment I'm working for the Italian Institute of Technology. Okay, I did my master's degree thesis inside the prosthetic center, so as a biomedical engineer. Then I obtained my PhD from University Campus Medico di Roma, but I was based as a long mission in the prosthetic center, so I had the chance for improving my my skills in the prosthetic fields and learn more and more and do my research on machine learnings and pattern recognition control system for upper limb prosthetics. And nothing. In the end, for getting employed in the prosthetic center, you need to undergo a public test, concorso pubblico. That is the way they are. I don't know. I'm not human resources. I don't know how these things are, but for what I know, that is the way. And it's very interesting. But there are partners. Our partner in research actually are universities or research institutes, and basically they if you want to operate, if you have the interest of working in this field, the partner can definitely offer you something. I don't know if they can actually. You need to ask them, but I suggest you to ask to all the partners and send emails and see what they reply to you. I try to answer to the question, but I take care of the engineeristic side. Is not the.
Okay, another question similar to this one. Okay, you talked about a fantastic research, fantastic experiments. Now, what's your ecosystem around you? Because I can imagine also some companies, startup, some new companies that to transfer your knowledge and to give you some idea. Because, for example, in our region, there is a big company that is working on prosthetics. Then I can imagine some cooperation, such kind.
Those are tough arguments because they involve the direction of the INAIL and the rulings. My director would have been here today, would have addressed your question perfectly. At the moment, I don't know what the position of the INAIL, the prosthetic center, is on startups and other innovation. Although all our research is published, so a startup can use it. There are patents, stuff like that. I don't know if there is any royalties and stuff like that. It's not my field, but it's published. You can see the result of our research, the research networks, and all the projects on internet, on the scientific papers, the most famous scientific journals, and you can follow actually the upcomings of the new project. Meanwhile, they're happening because the publication comes. Through all the projects, all the project activities.
Yes, why I'm the cluster manager of life science cluster Friuli Venezia Giulia. This is why my question about to connect such kind of experience. Thank you.
Yeah, they go above my role. Those type of questions. Any other question? Well, if there are no other questions, I'd like to thank you everybody for the attention and thank you again.